Today's video is about chapter 4.1, which is all about studying atoms. And you probably know what atoms are and have some general idea, but you may not know how the idea of atoms came about and how it was refined over time by some very important scientists. So that's what we're going to talk about today. So where did the idea of atoms come from? Well, way back in about 500 BC, which is over 2,500 years ago, there was this dude named Aristotle. You've probably heard of him, very smart, and he was what was called a philosopher. But back then, philosophers were really the scientists of the world. They would think about what they saw and hypothesize about why that might be true. They didn't have a lot of the technology or the resources we have to test those hypotheses, but they did come up with a whole lot of ideas. So Aristotle used to think that everything was made out of 4 elements, just like the 4 beeps you just heard for the beginning of class. And he thought that the 4 main elements were earth, air, wind, and fire. So those of you out there who like to watch The Last Airbender, this is where this kind of idea comes from. And Aristotle thought that these 4 elements could be broken down an infinite number of times, meaning no matter how small a piece of those elements you had, you could always make them smaller. But there was another ancient Greek, his name was Democritus, and he had the idea that you could only break matter down into its defining parts. So he had the idea that all matter was made of particles, and he called these particles atomos, or indivisible, meaning once you broke matter down into those pieces, you could no longer split them up. That was as small as you can get. And he thought that atoms in different states of matter had different properties. For example, he thought that atoms in liquids were really round and smooth, which gave liquids their flowing quality. But he thought that solids were rough and prickly, making them very rigid and hard. So this was really the beginning of the idea of atoms and building blocks of matter, which is incredible because this is so long ago. Skip ahead almost 2,000 years, and we get to this guy named John Dalton. At this point, science has pretty much accepted Democritus's idea that matter is made up of small particles, but John Dalton really took it another step further. And he discovered that compounds in gases always have a fixed composition. So that means that the ratio of substance 1 to substance 2 is always the same. For example, if he had a balloon full of carbon dioxide, he could separate the carbon and the oxygen and weigh them. And no matter how big a balloon he filled, the mass of the oxygen, or the amount of oxygen he had, was always twice the amount of the carbon, telling him that for every 1 carbon he always had 2 oxygens, CO2. And this led to him thinking, oh, well, that means that all matter is made up of individual particles, and when these particles combine in these combinations, that's how we get these different parts of matter. So there are 4 main components to Dalton's atomic theory, and this is really the basis for the atomic theory that we understand today. Dalton said that all elements are composed of atoms. Now, we're no longer talking about the elements of earth, wind, fire, and water. We're now talking about the actual elements of the periodic table. Obviously, they didn't know that all of them existed yet, but they had a pretty good idea of a big chunk of them. So he said that all elements are composed of atoms, these small particles. And all of the atoms of an element have the same mass. So every single oxygen atom had the same mass as every other oxygen atom. But every oxygen atom has a different mass than carbon or nitrogen or hydrogen or anything else. So if an atom has the same mass as another one, they have to be the same element. He also said that compounds, like CO2, have more than one element, and in that one compound, the atoms of different elements combine in the same way, meaning every sample of CO2 has a ratio of 2 oxygen to 1 carbon. They always combine in that ratio. So this is really where the idea of elements and compounds and basic particles came into play in a pretty rigorous scientific way, because this really came from Dalton's observations of gases and how they behave and what happens when he separated the different parts of those gases. Now, a little bit later, not too much later, but a little bit later, there was a guy named J.J. Thomson. And J.J. Thomson said that, okay, yeah, I like Dalton's theory that atoms are made up of small, or particles make up matter, but Thomson went a step further and said that atoms themselves can actually be divided. Atoms are made of smaller pieces. And he said, okay, these different pieces inside these atoms are negatively charged, and they're evenly spread throughout the atom, which is overall positive. This is usually called the plum pudding model. And you can see I have some pictures of plum pudding here. They look delicious. And you can think of this as the model of the atom for J.J. Thomson. All of the cakey bits were the bulk of the atom, and he said that was positively charged. And then all of the little plum pieces in here, those are the small negatively charged particles that just permeate through here. Now you may be wondering, how the heck did he come up with that idea? He didn't just think it up. He used the scientific method through observations of something called a cathode ray tube. So a cathode ray tube is this glass tube that has a little bit of gas in it, and when you pass electricity through it, you can see a stream moving through the glass, and it's glowing. So let me see if I can show you a picture. This right here is a picture of a cathode ray tube. You pass electricity from one end to the other, and as the electricity passes through that gas, you can see the gas glowing. Now, Thompson was observing this, and he found that if he brought a charged plate toward the side of that cathode ray tube, he could actually make the stream bend. So not only was that electric stream, that glowing stream moving from one end to the other, if he brought a plate near it, he could actually get it to curve. And because it was always attracting to the positive plate no matter which side he put it on, he determined that, okay, this stream of things must be made up of negatively charged particles, because a negative and a positive, when we're talking about electric charge, always attract. So if you have something that's attracting to a positive plate, that means it has to be negatively charged. He was able to figure out that these particles were not only negatively charged, but that they were also 2,000 times less massive than a hydrogen atom, meaning they have 2,000 times less mass than the smallest known atom. And because they're so ridiculously tiny, he decided, okay, these particles must be something that makes up an atom. It's a piece of an atom. And that's exactly where he got his plum pudding model. A positively charged atom with all of these negatively charged pieces in here, and these negatively charged pieces are what make up that stream that runs through the cathode ray tube. So here's another picture in this little drawing, and this is a picture of the cathode ray tube. So as the electricity is passing through, there's a positively charged plate here, and the stream will actually bend toward that positively charged plate, meaning this has to be negatively charged. So now we've moved from the idea of elements being made up of atoms and compounds being made up of multiple types of atoms to the atoms themselves being made up of different pieces. If we take it another step further, Ernest Rutherford came up with something that's pretty close to the model of the atom we understand today. It's not quite the same, but it's pretty close. So Ernest Rutherford decided that atoms are mostly made up of empty space. And the center of the atom is positively charged, and we call this the nucleus. So if I were to draw a picture of an atom, it would be something in the center, which is the nucleus, and then you would have other stuff around it. And this nucleus right here is positively charged, and all of the negative charges that Thompson said existed are still here. They're just all in the outside now. They're all around here. And to give you some perspective of the size of these things, if we were to put a marble in the middle of this football stadium, that would represent the nucleus of one atom. The outside of that atom would be the outside of the stadium around here. That's how small the nucleus of an atom is compared to the entire atom. So an atom is mostly empty space. It's like 99% empty space with negative charges in there somewhere. And all of the mass that we attribute to atoms is found in this tiny little spot in the center, our positively charged nucleus. And Rutherford came to this conclusion by doing something called the gold foil experiment. So he had a piece of really, really thin gold foil, and he shot some positively charged particles at it. And he thought, okay, well, if I do this, the particles are just going to travel straight through this, and I'll be able to see them hit the screen on the back. But that's not what he saw. He saw some of the particles pass straight through, but many of the particles were deflected, meaning they didn't have a straight path. They moved from one side to the other. And some of them even bounced straight back at him. What this told him was that the particles themselves, the atoms, had to have some solid piece that was positively charged so that it was repelling those positive charges being shot at it. So this right here is Thomson's model, and this is what he expected to see, Rutherford expected to see as the positive charges were moving through it. He thought the positive charges would go right through it, no problem, no biggie. But what he found was many of those positively charged particles went straight through, but some of them were deflected to the side, some of them bounced straight back, which gave him evidence for the existence of a tightly packed, very massive, meaning it has a lot of mass, nucleus in the center that is positively charged. So to kind of review, we went from the idea of Democritus and then Dalton that matter is made out of particles. It's made out of small pieces. Thompson built on that and said, okay, yeah, it's made of small pieces, but those small pieces have smaller pieces within them, and those smaller pieces are negatively charged. Rutherford went even a step further and said, yeah, those negatively charged pieces are there, but there are even more tiny pieces inside of this particle. And they're so ridiculously small, they reside in like the center 1% of the space of that thing. What we're going to talk about next week is the Bohr model and the quantum cloud model. These are a little bit more complicated, but they build off the ideas of Dalton, Thomson, and Rutherford to give us a more accurate picture of what's going on. Really what this leads us to is the evolution of the atom to how we know it today, having a very dense positively charged nucleus in the middle and all kinds of negatively charged electrons around it.